Hey, what's up, guys? This is Cheng here. So today, before going to bed, I would like to talk about this week's weekly contest, 1,584 minimum cost to connect all points. It's a medium problem. I think it's a good problem anyway. So you're given like an array point representing integer coordinates of some points on the 2D plane. So we have a basically a, a array, a list of a list. Each element represents a point on this 2D plane, and the cost of connecting 2 points, these 2 points, is the Manhattan distance, which is the absolute difference between the x and the y's. Okay, and it asks you to return the minimum cost to make all points connected. All points all points are connected if there is exactly one simple path between any 2 points. Okay, and for example, the first one, the points. So we have like 5 points, and the minimum cost to connect all the points is this one, which is 20. Okay, so I mean, the thinking I process for this problem, every time when you guys see like try to like connect the points, right, to this is a graph, right, basically. This is like the or this one is like minimum spinning tree, right? Basically, each one between any 2 points, there is only one edge to connect them. And there's also like an algorithm called cro crosscal, if I'm not mistaken. Basically, it's the same idea actually as a union find. Basically, as you guys can see, basically we're trying to follow what the problem is asking us to do, right? We're trying to connect several points together, which is it's a perfect fit for the union find data structure. Okay, basically we will have like we'll try to union find some edges, sorry, some points in a certain order so that we can get like the minimum cost. But now the question comes down to how can we get the minimum cost? Okay, so for that one, basically what we need to do is we just need to pre-calculate all the distances between each of the nodes, and then we'll be basically it's kind of like a greedy idea here. We'll be sorting those like those edges, right? So the edges has a like starting point and ending point, right? Have two points, and then it also has a distance. Basically, we will be trying to union find those 2 points whose distance is the least, so that we can it's guaranteed that we can get the minimum cost. Okay, and so here's comes the beauty of the union find, right? Basically, as long as every time when we try to union two points from an edge tuple here, I mean we can simply use the union find to check if those two points have already been union before or not. And we only add the cost when those 2 points had not been union before. Okay, that's the That's the beauty of the unified like data structure. Okay, cool. I think that's pretty much the idea behind this problem. And let me try to implement the solution real quick here. So, like I said, to do the union find, right, we need to do like define the data structure here. Okay, so and I'm going to just use the simplified version of the union find. Basically, for the union find, remember we always need to like have like the parent at the beginning, right, each of the elements pointing to itself, okay? Because we have n points, and basically we're using the index for each point to represent the index of the point to represent the node itself. That's why we do a range n here. And then we have a find, right? Find, and with the find, we use the the path compression. Okay, if the parents x, right, that's not equal to the x, then we do this equals to the find parent x, okay, and then in the end we simply return the parents. You know, for those who is not familiar, still not familiar with the union find template, I, I suggest you guys try to try to understand the basic union find templates first from maybe from anywhere, maybe for example the Wikipedia. I'm pretty sure you can find a lot of articles regarding how to implement the union find data structure. So but that's basically the find part, where basically as long as the parent is not the same as the x itself, basically as long as x is not the root, right? Because at the root the root is always pointing to itself. Basically, if the current one is not the root itself, we keep looking for its parents. Okay. While keep looking for it, we're trying to like doing the path compression by doing this until we reach the root. Then we simply return the root itself. Okay. And then for the union, right? For the union here, we do x and y. Okay. So for the union here, you know, we're gonna root one equals to the find x, okay, and the root two equals to find y, okay, and we only do the union whenever the if r1 is not equals to r2, and then we do the union, okay. And in I mean, so for the complete union find structure, ideally we should also have like a ranks, you know, ranks equals to for each of the ranks maybe after zero, okay, you know, something like this, you know, basically uh, based on the current ranks we'll be assigning the roots from one to the others. I mean, just to make sure so that we can basically balance the trees a little bit better, which it can also improve the uh, the time complexity. But you know, basically what we're doing here, basically if the ranks uh, R1 is greater or equal than ranks R R2, something like this, right? Basically, we'll assign the parents of R2 to R1, something like this. The other, or if otherwise, we assign the parents R1 to R2. But for the simplicity case here, I'm going to remove the ranks here, which means uh, I'm always assigning the R2 to R1, or always assigning R1 to R2. It doesn't really matter. For now, I'm just assigning this one here. Okay, that's why I'm saying that. Why I said I'm using a simplified version. Okay, so basically that's the two basic operations for the union find. And now since we have a union find structures, and we can simply construct the edges, right? Basically, we have a sim one path between the 2 points. Okay, probably I'm gonna use the path here. Okay, and to construct the path, right? In, in range n, basically we're going to calculate uh, the edges for between each of the, the each of the two nodes. To do that, I'm also going to define like helper functions to help us define calculate the distance. Okay, so this one is pretty simple, right? P1 0 minus P2 0 plus ABS P1 1 minus P2 1. Okay, so I plus 1 dot n, right? That's how we select all the pairs, right? Because the sequence of the pair doesn't really matter, so that's why we can simply do the for loop here. Okay, and the distance, right? The distance is what is this, right? So the get distance uh, points I and points j. Okay, so with each of the edge of the pair, the points pair here, I'm going to add that dot append. Okay, append to what? So the first one is distance. The reason we put the distance at the first element is because we want to sort by distance later on. And the second one is I and j. Basically, we use the index, right? The index uh, of the 2 points to represent the point itself. So that's when we are going to use, and we'll be using the index and to do the union and find. Okay. So that's that. Now we have all the paths here. Now I just need to do the sort. Okay. So now now we just start processing the path from the smallest to the biggest. The distance and the P1 and P2. Okay, from path. Sorry, in path. Okay. And like I said, uh, since okay, sorry, I'm also going to create define the answer here. Basically, we only going to add this distance to the answer when we actually doing the union, right? If we don't need to do the unions, we don't add the distance. So the way we're checking it here is that we have to utilize this one here. Basically, if the R1 is not equals to R2, then this is when we do the union. One way of doing this is we can simply return a flag from the union here. Basically, if we do a union, we return true here. Otherwise, we just return false. Okay. So this way we can just simply use this union to check if we have if we have ever if we really did a union or not. Basic. So union, okay, P1, P2. Okay, basically if the union P1, P2 return a true value, then we know, okay, we did a union, so that we can just add the distance. Okay, otherwise we don't do it, and then we simply return the answer here. Okay, yeah, I think that's pretty much it is. I think let's try to run the code. Okay, so the test case passed and submit. Cool. So it accepted. It's not the fastest one, but I think it's the most easiest way. The most easy. I mean, it's the easiest way of solving this problem, at least for me. Because and the unifying. I mean, it follows the intuition, right, of this problem. Basically, we need to use a unifying to help us to determine uh, when to uh, when to union those two nodes, because the way this problem is asking us to connect those two other points, it's essentially the same thing that the union find is doing here. So it's just like as if we were doing the union find, but with a cost of each union. Basically, that's the nature of this problem. So next time when you guys see like a problem that asks you to connect different points or different parts or components, try to use the union find. Okay, and also, and after the union find, it also asks us to find the minimum cost. Okay, so in order to find the minimum cost, we need to pre-calculate all the possible paths first with the distance. Okay, and then we just sort. We sort by the distance so that we always pick the minimum distance and then to do the union find. And when we do the union find, we do this, right? We we union, and then whenever there's a union really happened, then we add the distance to the answer. Otherwise, we know that okay, those two nodes, those 2 points had already been unioned before, so there's no point of union connecting them again. Okay, I think that's that's pretty much it is for this problem. Yeah, and okay, cool. Thank you so much for watching the videos, guys, and I hope you guys like the video. Stay tuned. See you guys soon. Bye bye.